first section, curvilinear motion of particles. Curvilinear motion of particles. Curvilinear motion of particles. Now, the last class, we discussed rectilinear motion, which means that the object was moving on a straight path, okay? Or the trajectory of motion was a straight line. Now we want to look at motion in curves. Okay, a straight line is also a curve, anyways. So curvilinear motion means that the trajectory of motion is different from a straight line. That is, it's not a straight line. So it could be just any other thing. Okay, so to do this, to analyze curvilinear motion, we can use different coordinate systems. The one thing you should notice here now is that we cannot use a single axis to define curvilinear motion. Do you understand what I'm saying? Okay, the last one we talked about rectilinear motion. We used a single axis, maybe just x-axis or just y-axis, to define the motion, and that was okay. But here, because the motion proceeds in not on a single straight path, then we have to use more than one axis. Anyway, do you understand what I'm saying? Okay. For instance, in the case of rectilinear motion, because the body is moving on a straight line, I can say this is the path followed by the body, and to define the position of the object, I just need to get x coordinates at any point or at any time. Okay. But in the case of curvilinear motion, since the path is not a straight line, then it's not sufficient to use a single axis. So I can use a 2D coordinate system, like I have x-axis and y-axis. For instance, the projectile motion problem, we have this kind of trajectory. That tells you that we could not have used a single axis, say x-axis for instance, to locate the position of the object. We will have to also simultaneously describe its y coordinate. So if the object is at this point, I will say this is its position. Its position will be defined by x and also y. Is it clear? If the object is at this point, same thing happens. I will trace out its x coordinate, trace out its y coordinate. So that will be at x1, say y1. You get that? Okay, so that is how I can sufficiently describe its position at every point in time. I can also use a three-dimensional coordinate system where I have x, y, z. Okay, you can still remember how we dealt with this last semester, or this dealt with us last semester. So you have to locate an object in space. You can say this is its position. With respect to time, I will say that the position will be given by the position vector r. Let's say it's x coordinate, y coordinate, and z coordinate. So I want to locate the object in space. So curvilinear motion means that it proceeds on a path or a curve other than a straight line. Is that clear? Okay, so it is not a straight line. Alright, so how do we analyze these kinds of motion? So listen now. For both illustrations I just do now, we have actually used a rectangular coordinate system, or what we call a Cartesian coordinate system. Have you now? We can also use the other types of coordinate system. We can use the polar coordinate system. We get to talk about it later. We can also use what we call the normal and tangential coordinate system, or normal and tangential component. Right? So in the polar coordinate system, we talk about radial and transverse components. So we'll get there. But we'll start with this. So this means that in this case, I cannot tell the position of the object by just saying that it was at the point x and then the position changed by delta x. So this was how we started the last one, what we talked about rectilinear motion. So in this case, I'll be interested in the position vector. Okay, to describe the position of the object, I will have to use the position vector r. That this object is located at so points. That means that if I'm dealing with two dimensions, r will be defined as xi plus yj. So the x coordinate plus the y coordinate, the vector. Is that clear? And if I'm dealing with 3 dimensions, I will also have the z component, or z coordinates. Does that make sense to you? So that means in this case, the position here is going to be a vector. Do you get that? Literally a vector. You understand what I'm saying? In the last one we did rectilinear motion, we can say it's just an algebraic relation and we differentiated. Okay, and we were able to tell the direction by looking at the sign of the quantity, whatever you get from it. Maybe acceleration, velocity. If you want to know the direction, you look at the sign. But in this case, sign will not be sufficient to tell the direction, except we have the signs of all the components that can tell the direction. Is that clear? Okay, so please pay attention. So in this case also, it may happen that listen. So it may happen that an object is initially located at a position R and later located at some position R prime. Okay, and we may also be interested in, please pay attention, we'll also be interested in getting the velocity of the object. The velocity is defined similarly. It is defined as the derivative of the position coordinate with respect to time. Now a position vector with respect to time. Does that make sense to you? Okay? And we also similarly define the acceleration. We say acceleration will be equal to this derivative of the velocity. Now they are vectors, literally vectors. Okay, so this is going to be derivative of velocity with respect to time, which is the square of r position vector c square. Does that make sense to you? Okay, so in this case, how do you get the direction of velocity? Or what does it mean when velocity is positive or negative? We cannot easily interpret that from here. Unlike the other one where we just said, if velocity is positive, that means x is increasing, it's going forward. If velocity is negative, that means x is decreasing, it's going backward, but here, we don't have any such thing. This is a proper vector, and for a vector, you can only get its magnitude and direction. Do you understand that? So from its components, you will find out what direction it is facing. Is it making sense to you? But the direction of the velocity is always tangent to the path followed by the body. Okay? That is velocity vector, this velocity vector. That is, if I come here and I evaluate the velocity at this point, it is going to be tangent to the path followed by the body. If I evaluate the velocity at this point, it will be tangent to the path followed by the body. If I evaluate the velocity at this point, it will be tangent to the path followed by the body. So velocity is always in the tangential direction. Is that clear? Velocity is always in the tangential direction. Velocity is always in the tangential direction. I said velocity is always in the tangential direction. I'm saying it again. Velocity is always in the tangential direction. In other words, velocity is always tangent to the trajectory of motion of the body. Velocity is always tangent to the trajectory of motion of the body. So, you know what trajectory is? Trajectory is the path followed by a moving body. That means velocity is always tangent to the path followed by a moving body. Does it make sense to you? It is always tangent to the path followed by a moving body. Look at it. If I want to illustrate this in reality, look at it. If I am moving in, let's say I want to move in a circular track. Okay, look at this circular track on the ground. I want to move in this circular track. You know what I have to do? Velocity simply means that, normally from rectilinear motion, direction of velocity is direction of motion. If I want to move in this circular track, you know what I have to do? If I stay here and I want to move forward, when I stay here, I'm actually facing the direction that is tangent to this curve at this point. This is going to be like this, That's where I'm facing. That's my direction of velocity. It's tangent to the circle, If I want to maintain the circular track, you know what I have to do? Immediately I come here, I have to change my direction. Is it clear? This is still going to be what? Tangent to the circle at that point. Is it clear? So, no matter how you go, so far you want to maintain the track, it has to be tangent to the track at that point also. Do you understand this idea? Its velocity is always in the tangential direction. But acceleration is not in the tangential direction. Acceleration does not have a definite direction. It depends on whether the velocity is increasing or decreasing at a particular direction or in a particular direction. So acceleration has no definite direction. So acceleration could be tangent. Okay? Acceleration could be tangent to the path followed by the body. Okay? It may also be normal. Do you understand that? The path followed by the body. And it may be both of them. That is, we may have both normal component and tangential component. So we'll talk about that in another time. But just know that The tangential direction is the direction of velocity. Okay? So that means if I am given the position vector as this, then if I want to get the velocity vector is going to be equal to the derivative of this. Now look at something. If you want to differentiate this expression, we say dt of xi plus yj plus zq. Please pay attention to this. Okay, I know normally we would say that this is I, the x, the t, abi, plus j, the y, the t, plus z, plus k, the z, the t. Okay, which is fine. But you should know something here that it is not a blanket statement, so to speak. Why that is correct here? Because as we get to see when we get to some other coordinate systems, unit vector is not always a constant. In this case, unit vector is a constant vector in that it has a constant magnitude of 1 and it has a constant direction along the x-axis, for instance, or along y-axis or along z-axis, and it stays that way. Is that clear? Okay. That's what we call when we have an inertial reference frame, where the reference frame the system of axis is stationary, that is, it does not move, or it only undergoes translation. That means it only goes on the straight path. Okay? When you have that kind of situation, that means that the orientation of these unit vectors will never change. Do you understand what I'm saying at all? If the unit vector is facing this direction, if this is x-axis for instance, that will continue to be the direction of our unit vector I. Is it understandable? So far, the orientation of the coordinate system does not change. Is that very clear? That's what we call an inertial reference frame. Okay, so pay attention now. So normally, this is the product of two functions. I think this was actually dependent on t. That is, if I was not a constant vector, for instance, I would write this as x, the I mean, dt plus I dx dt, abi now, plus y dj dt plus j dy dt plus what now? Z dk dt plus k dz dt. Does it make sense? Alright, but now we know that we are dealing with an inertial reference frame where the reference frame of the system of axis is stationary, or it can only translate. So in such a situation, the orientation of these I, J, K vectors will not change. We also know that they have unit magnitude. So it is a vector. The magnitude of the vector does not change. The direction of the vector does not change. And the vector is a constant. Does it make sense to you? Because the vector is a constant, I know that the derivative of the constant is 0. So because of that, this will be 0, okay, and then this will also be 0. So that is why we write and correctly so I dx dt plus j dy dt plus k dz dt for the velocity. Does it make sense to you at all? Alright, so that's why we can write velocity that way and say it is correct. Look at this now. So that means when I come here, listen now. So when you take derivatives with respect to time, okay, usually in this talk we will use this notation. Instead of having the x dt, you can put it in shorthand form as x dots. Is it clear? So when you see x dot or v dot means derivative of v with respect to time. Is that clear? R dot means derivative of r with respect to time. Star dot, you come across it later. Typically something like that in page 104. So it's derivative with respect to time. Is it clear? Okay, so that means I can write velocity as r dots, abi? Because I put the dot here, I put the arrow below, which is the same thing as what? X dot I plus y dot j plus z dot k. Does it make sense? Yeah. So similarly, I can write acceleration as v dots, okay? Which is the same thing as r dot dot. Is it clear? R dot dot simply means I'm taking the derivative of r twice. Is it clear? Okay, just the square r with t square. Alright, so this is the same thing as writing x dot dot, or let's say this one. Let's say this is v sub x. If v sub x is this, v sub x I plus v sub y j plus v sub z k. Now, x component of v that's our x dot. Y component of v, that's our y dot, and z component of v, that's our z dot. So I can write this as vx dot I plus vy dot j plus vz dot k, which I can also write as x dot dot I plus y dot dot j plus z dot dot k. Do you understand that? You get it? So that can be as easy as that. So now we want to see an actual application of this. We usually apply this to analyze projectile motion problems. Projectile motion problems. Okay, where we have them in 2 dimensions. So usually, what we do when we want to analyze this kind of motion is to say that is why we're using this coordinate system, is to treat them as though, listen, we treat the respective components as though they are independent of one another. That is, I will analyze the motion as though it can actually undergo motion in the x direction all alone without simultaneously undergoing motion in the y direction. Is it clear? That is, I will treat the motion components as though they are independent of one another. Of course, I know they are dependent on one another. So, look at this. So, an example of where we apply this is in projectile motion movements. So, projectile motion. So, we've done something like this in the past. So, projectile motion. That's a kind of. So, I say that a projectile motion is a two-dimensional curvilinear motion. Two-dimensional curvilinear motion whose trajectory is a parabola. You get that? So, it goes on a parabolic path. So, the trajectory is a parabola. So, you know examples of projectile motion before now. So, you have something like this. So, you can see that the motion simultaneously proceeds in the x and y direction. Okay? It proceeds in the x and y direction. That means in this case, I can write or I can get the position at any point. I can write it as xi plus yj. Is it very clear? Alright. So, listen now, listen. Now, when projectile motion occurs under normal condition, that is without air resistance and all of that, which is an assumption, the fundamental assumption we usually make here, it will happen that the vertical components of motion, I said something just now, I said we will analyze them as though the 2 components of motion are independent, okay? So the vertical component of motion is uniformly accelerated motion. We will analyze the vertical component of motion as motion under gravity, which is uniformly accelerated motion with acceleration equal to g. Now, that's acceleration of free fall. Is it clear? What we call acceleration due to gravity. And then the horizontal component of motion is uniform motion. That is, the horizontal component of motion is motion with constant velocity. Does that make sense to you? Alright, so in this horizontal direction, what we have is uniform motion. We have made this difference several times. So this happens to be uniform motion. And what we have in the vertical direction is uniformly accelerated motion. Uniformly accelerated in this direction. Okay. So listen now. So for uniformly accelerated motion in this vertical direction, for the y component of motion, happens that so pay attention now, pay attention to this. So before now, when you analyze when you analyze motion under gravity, you used to say that if it's going up, the acceleration is negative, have you? If it's coming down, the acceleration is positive. Have you done something like that before?
Yes.
In secondary school.
Yes.
Yes, secondary school, you did that. If you didn't learn that in secondary school, I wonder what you learned in secondary school. Who could be that? Okay, so listen now, but we will not do that here. That's a very simple way of presenting it to you. But now, the reason that was correct, yeah, if you do calculations with that, it's correct. In fact, this projectile motion we want to do, if you still remember all those equations of projectile motion, all those square sine, sine, theta, you still remember them and you apply them, yeah, properly. So you can use them to solve almost all the problems you come across. Just that you're dealing with theory questions and you expect you to analyze this properly. You get that? You're not exposed to a better understanding of this. So look at this now. But that is not so. Listen now. Why is that the case? Because we will analyze motion here using a coordinate system. Abi? So our coordinate system already tells us what is positive direction and what is negative direction. Is it clear? So as far as the y component is concerned, the upward direction is positive, Abi, and downward direction is negative. Abi now? So it is the reality that if the body, when the body is moving upwards, it's going to be moving more slowly. Abi now? Till it gets to the maximum point and the velocity becomes 0 and then it drops down. Is it clear? So that means when it is going upward, it will be moving more slowly in the negative, in the positive direction. Abi now? And when it is coming downward, it will be moving faster, but now in the negative direction. Either ways, both are negative acceleration. Does it make sense? I've told you that when acceleration is negative, it could mean something. It could mean that the body is moving faster in the negative direction or more slowly in the positive direction. Is it very clear? So that means for all cases here, the acceleration, that's of course the y component. For the y component of motion, for the vertical component of motion, for the vertical component of motion, acceleration is always equal to minus g. Is it clear? Always equal to minus g. Okay, so the position coordinate takes care of whether it is going upward or coming downward. Is it clear? If it is going upward, for instance, the change in position is going to be positive. If it is coming downward, the change in position is going to be negative. Is it clear? So whether it is going upward or coming downward is taken care of by the position coordinates. Is it clear? Alright. So that's that about that. So that means that you have motion with constant acceleration. This acceleration of 3-4. Whereas for the x component of motion, there is uniform motion. That means that velocity in the horizontal direction remains constant. Okay, so in this direction, velocity is constant. If velocity is constant, that means acceleration is Abi. So I know this is y component of acceleration. So that means the x component of acceleration is direct. Is it clear? Is this clear? Yeah. Alright. So if the body takes off, for instance, we used to do something like this. So if the body takes off at a certain angle to the horizontal, let's say it takes off at a certain angle, say theta to the horizontal, and it took off its initial velocity v0. That's the magnitude of its initial velocity. You know, you would be able to resolve this into horizontal and vertical components. I think we have learned how to resolve vectors into horizontal and vertical components already. So this is going to be your v0 y, the y component of the initial velocity, and this will be your v0 x. Is it clear? That's the vertical component of, the horizontal component. So we're going to have the initial components of velocity, initial velocity. The x direction is going to be equal to what? Initial velocity v0 cos theta. This is going to be v0 cos theta. And for this, we're going to have the initial component of, or the initial velocity, the y direction will be v0 sin theta. Does that make sense to you? Do you understand that? Alright. So we know that, listen now, so you should remember I said something that we're going to treat the components as though they are independent. Abi? So I'll analyze the x components and analyze the y components separately. But I know that they occur simultaneously. Abi now? That means time is common to both of them. Is it clear? Do you understand what I just said now? Both of them occur simultaneously. So what is common to both of them, or what links both of them is the time. Is it clear? So that means, listen now, I know that the vertical component of acceleration is uniformly accelerated motion. Abi? So I can use my equations of uniformly accelerated motion. I also know that this is uniform motion. That means I can use my equations of uniformly accelerated motion with acceleration equal to 0. Does it make sense here? Okay? So you will recall that for our uniformly accelerated motion, v is equal to v0 plus at, x minus x0 is equal to v0 plus 1 over 2 at squared. We say v squared is equal to v0 squared plus a x minus x naught. So x naught was were used to actually represent the position coordinates. Happy now? So when dealing with the y component, that means I'll be using y and y naught. Does it make sense to you? Alright, so if I want to get the y coordinates at any point, I would use y is equal to y naught plus v naught y, is it clear? Because I'm dealing with the y component, plus 1 over 2 into a y c square. Does it make sense to you? Do you understand that? Okay, v naught y t, yeah, thank you. So this is going to give me y minus y naught equal to v naught y, abi, c, minus 1 over 2 g c square. Abi? What have I done? dy is g. So if I want to analyze motion in this direction, I can always use this motion. Does it make sense? You know, when I look at uniform motion, when I substitute acceleration equal to 0, if I put in acceleration equal to 0, that just tells me that final velocity is same as initial velocity. Yes, I know. That's what constant motion. I mean, that's what uniform motion is. You get that? That is of no significance. If you substitute here, you're going to get this to be 0, so you're going to get x minus x naught is equal to v naught t. Is it clear? So that means that for this component, I will use x minus x naught is equal to v naught x multiplied by t. Is it clear? So v naught x or vx or whatever is always constant. Have you know? I know the velocity in the x direction is always the same. Do you understand that? That means that if I'm going, that means when I get here, if I get here and I want to get the velocity here, its x component will still be the same thing as v naught x. Is it clear? Because even if I'm here and I want to get the velocity here and the velocity at this point, its x component will still be v naught x. Is it making sense? So the only thing I will have to worry about is to get the y component of velocity. Does it make sense? Of which, if you want to get the y component of velocity at any point, you can always use this vy will equal to v naught y minus gt. Does that make sense to you? Whereas the velocity for this is always constant. Velocity at any point is always equal to the initial velocity. So vx, v sub x is always equal to the initial velocity. Does that make sense to you? Do you understand this? Velocity is always the same. Is it clear? Is this clear? Alright. So that means if I want to do that, I can say, listen. From here I know if I want to find out, maybe I know initial position or initial velocity, I'm able to get that. I can make t, okay, the subject of the formula a, and substitute into this expression. You understand what I'm saying? When I make t the subject here, I'll put that t into this. Okay, for instance, if I know the initial velocity v naught, this is my initial velocity v naught. I know I can get v naught y from it, and I can get v naught x from it. When I get all of those, I will use this equation. Okay, when I substitute to this equation, I'll get x. I'll get t in terms of v naught and x. Okay, and I'll put it into this expression. So I'll be able to solve for the other one. Is it making sense to you? So that's that about that. It's quite easy to do. So we're going to solve problems using this idea. So just know what this thing is. So look at something now. You notice that, hello, please pay attention now. You notice that when this body, when this body is at its maximum point, what do you think is going to happen? When it is at its maximum point, what do you think is going to become 0? The velocity is going to become 0. Is that a correct statement? Final velocity will be 0. Is that a correct statement? Think about it. Which of the velocities will be 0? Is it the vertical or horizontal or both of them? Vertical. The vertical component of velocity will be 0. So it is wrong to say the velocity will be 0. The velocity cannot be 0. Do you understand that? Why is it so? Because this is not motion under gravity where it just goes vertically. Do you understand what I'm saying? If it's just going vertically, we say the velocity becomes 0 and it drops. But here, the velocity never becomes 0. Is it clear? If the velocity, so it is still moving in this direction, even when it gets to the maximum height. Is it clear? Right. So, because we have said the horizontal component of velocity is constant. Is it clear? So the velocity doesn't become 0. What becomes 0 is the vertical component of velocity. Okay? Please take note of that. Alright, so let's solve some problems using all of these ideas and see how it works. Okay? How it works. 11.89. The motion of a particle is defined by the equations. Are you all there? Yes, 11.89. 9th equation. The motion of a particle is defined by the equations. I hope you all have that. You have someone beside you with it. You don't have it. 11.89. The motion of a particle is defined by the equations x equal to, can you see that? Listen, please, listen. X equal to 4TQ plus blah blah blah, and y equal to, can you see that now? So this is different from rectilinear motion. If it were rectilinear motion, you just be given x only or y only. Is it clear? So when given x and y, that tells you that it is curvilinear motion. The motion proceeds simultaneously in both x and y directions. Is it clear? Right. So this is the general case of it, where x and y are expressed in millimeters and t is expressed in seconds. Determine the velocity and acceleration when t equal to 1 second and b when t equal to 2 seconds. So listen very well. So the chart here is that they just told you determine the velocity and determine the acceleration. You may be tempted to just substitute, get your answer, and then put in the terms of x and y. I mean the x component and y component. No, the proper thing to do is get the get the magnitude and you get that. Get the magnitude, then get the direction. Is it clear? Because you have the x component and y component, so you can get the magnitude and the direction. So let's do this together. So this is a general motion problem in 2 dimensions, not projectile motion. When you get projectile motion, you see. Okay, so this is x equal to 4t cubed minus 5t squared plus 5t and y equal to 5t squared minus 15t. So you have this, they said x and y are expressed in millimeters and t is expressed in seconds. That means when I get my results, they're going to do in millimeters per second and millimeters per second square respectively. You get that? So I'm going to do this for t equal to 1 second, so you do for t equal to 2 seconds. So I'll be given x. I know that, listen now, r, the position vector, is equal to xi plus yj. Abi? Do you understand that? So from this expression also I can get, I know that d is going to be equal to x dot I, Abi, plus y dot j. And I know that what? Acceleration is equal to x dot I plus y dot j. Does it make sense? So from what I have been given here, I can get x dot and y dot. So I know x dot is going to be equal to what? Derivative of this with respect to time. That will be 12t squared minus 10t plus 5. Is it clear? And you understand what I'm doing? You understand that? Yeah. Alright. So y dot is going to be 10t minus 15. And then I can get x dot dot. So I can do that right here. X dot dot, differentiating this again. This will be 24t minus 10. And then y dot dot, differentiating this again. This will be 10. Y dot dot equals 10. So therefore, I can write expressions for v and a. So velocity is going to be equal to 12t squared minus 10t plus 5 I plus 10t minus 15j. Does it make sense? Then acceleration will be equal to x dot dot, that is 4t minus 10I then plus 10j. Is it clear? So this already tells you something. If you didn't notice, that means this question could also have been given this way. You may have been given, instead of giving you x and y separately like this, the question could have been written in this form. R equal to 4t cubed minus 5t squared plus 5t I plus 5t squared minus 15t j. So this actually means this. Is it clear? Anyhow it's done, so don't change it out. Alright, so we're going to go. That means that at t equal to 1 second, just substitute 1 here. So that means at t equal to 1 second, at t equal to 1 second, our velocity will be equal to, and the first part, at equal to 1 second. Let's put 1 here. It's going to be 12 minus 10 plus 5. What is it? 12 minus 10 plus 5, 7. So this is going to be 7i. This 10 minus 15. Minus 5. This will be in millimeters per second. And then acceleration is going to be, what is this? 24 minus 10. That is 14. This is going to be 14i minus, plus 10k millimeters per second squared. So we can now get their magnitude and direction. Does it make sense? So that means, in this case, the velocity is given by this vector. Its x component is positive, its y component is negative. Do you understand what I'm doing? Do you understand this? Yes. Alright, so I'm going to have something like this. X component is 7. So I can say, let's make it a bit longer. And this one is 5. The negative direction. So the direction of the velocity is going to be this way. This is going to be the direction of the velocity. Is it clear? Okay. And that means you will get the direction. For instance, the angle it makes with the x-axis, angle theta. Is it clear? So I'll find out what that is. And then I will get its magnitude, v. So I know v is going to be equal to the square root of 7 squared plus minus 5 squared. Okay, so whatever that is, and I can get theta equal to tan inverse of opposite 5 I just 11 points. 11 points. What's the answer?
That one is 74 now. 8.6.
8.60 mm per second. This one? 35.5. Alright. So therefore, I'll say that the velocity of the body equals to 8.60 meters per second. In direction 5 degrees to the horizontal. 35.5. So that is the body is moving to that direction. You can do the same thing for the acceleration. You can do the same thing for acceleration. Let's do that together. So I'm going to do it for 2 seconds. So for the acceleration, it has positive x component and positive y component. Can you see that? So that means we're going to have something like this. X component is 14, y component is 10. So this is going to go this way and this way. It's going to be the acceleration of the magnitude of the acceleration. I'll find out the angle, say, theta 2, let's say this is theta 1, that it makes with the x-axis. So that is going to be the acceleration. That's the magnitude of acceleration is going to be equal to the square root of 10 squared plus 14 squared. So whatever that gives us, and theta 2 is going to be equal to the tan inverse of opposites, that's 10 over adjacent, 14. 10 over 14. So what does it give you? 17.2. 17.2. 2 what? Millimeter per. 2 what? 2 what? The result.
204. 205.
205.
Yes.
That's 17.21 millimeters per second squared. Right. What does this angle give you?
35.5.
So therefore, acceleration equals to 17.21 mm per second squared. The direction is 35.5 meters. You can see that the you can see that the acceleration and the velocity are not in the same direction. Can you see that? Acceleration and velocity are not in the same direction. Did you notice that? They are not in the same direction. They are not in the same direction. Alright. So you can do for t equal to 2 seconds now. Tell me your answer. 33.4 and 39.3. Alright, let's move on. Look at the next one. The motion of a particle is defined by the equations x equal to 2 cos pi t and y equal to 1 minus 4 cos pi t plus 2 pi t, where x and y are expressed in meters and t is expressed in seconds. Show that the path of the particle is part of the parabola shown, and determine the velocity and the acceleration when t equal to 0 and b t equal to 1.5 seconds. So pay attention, please. Pay attention. We want to establish first that the path is what has been defined here, but it's quite easy to do. What you're going to do is to just make a substitution. Look at this. Okay, look at the dot, please. X equal to 2 cos pi t. Y equal to 1 minus 4 cos 2 pi t. Right. That's how the positions have been defined. Please pay attention. So we want to firstly show that, listen to this, the path of the particle is part of the parabola shown. If you look at the parabola given to us, the equation of the parabola given to us is y is equal to 5 minus 2x squared. So how do you show that this equation is part of the parabola? I mean, to show that this equation satisfies this parabola. Does that make sense to you at all? So you get that? So that means we should have y plus 2x squared to be equal to 5. Is it making sense? Is that clear? So we take the right hand, the left hand side, taking the left hand side and substituting the equations. Do you understand that? We verify that it's actually part of this parabola. Does it make sense to you? Taking the left hand side, you can just put everything together and take this one is 0. So this is going to give us L. We're going to have 2 into y, our y comes first. Y is 1 minus 4 cos 2 pi t, okay, plus 2 into x squared, that's 2 cos pi t all squared. What does this give us? This is going to give us 1 minus 4 cos 2 pi t plus, this is going to be 2 multiplied by 4 cos squared pi t. Is it clear? Okay, so this is going to give us, I don't know, there's 2 here. Okay, this one doesn't have. So we're going to have that, we can simplify this, but that's going to be 1 minus 4 cos 2 pi t plus, this is going to be what? 8 cos squared pi t. So have them in a form that we can put together. You know, this is, we will only 2 to that. This one has 2. So I can simplify this one that has 2, so that it's just in the form of pi t. Is it making sense? Don't forget that cos 2 theta, I remember this, cos 2 theta, the same thing as cos theta plus theta, which is the same thing as cos squared theta minus squared theta, which you can write as cos squared theta minus 1 minus cos squared theta. This is going to be 2 cos squared theta minus 1. So I can put that right here. This is going to be equal to 1 minus 4 into cos squared pi t minus 1. Do you understand that? Then plus 8 cos squared pi t. This is going to be equal to 1 minus, this is going to be what? 8 cos squared pi t. Then this minus 4 times minus 1, that is plus 4. Plus 8 cos 8 cos squared phi t. So this we will cancel this. So I have 1 plus 4. Does it make sense? This is going to be equal to 5. Does it make sense? Which is what you have on the right hand side. Is it clear? That's what we have on the right hand side. It satisfies the equation of the parabola. Does it make sense? It satisfies the equation of the parabola. So that parabola defines some portion of motion of the sphere. Is it clear? Is it clear? And the second part says we should determine the velocity and acceleration when t equals to 0. I believe we can do that. So just differentiate the way we did the first one. Do you understand that? Just differentiate and get the velocity and acceleration when t equals to 0. So as we did the first one, we're going to do the first part together, then do the next one. So this is going to give us, we have been given that x is equal to 2 plus pi t and y is equal to 1 minus 4 plus 2 pi t. So we can differentiate x dot to be equal to the derivative of this
minus 2 pi sine phi t.
minus 2 pi sine pi t. And this will have y dot, the derivative of this, that will be 8 pi, you get that? I made this right here, sine pi t. Is it clear? Then you can get x dot dot. Why? Because we need the acceleration also. Is it clear? If you were asked to find only velocity, there will be no need for this. Do you understand that? So this is going to be equal to. Okay, this is 2 pi.
No, the y side.
Okay, the y pi. Thank you. Sine 2 pi. Yeah. So this is going to give us x dot dot. I'm going to add this to be minus 2 pi squared plus pi t. And y dot dot will be equal to 16 pi squared plus 2 pi t. Alright, so we are going to go. So we can also evaluate them at t equals to 0. See that? So A, on the A part, at t equals to 0, we have, I don't need x and y, do you get? I just need velocity and acceleration. So I think we will have to find the position at that t equals to 0. I will just substitute them in x and y. See that? I'm doing the same thing we did earlier. The only thing here is that I want to get all the variables first. So that when I write out A, I'll just put it in. When I write out B, I'll just put it in. See clear? So that's going to give us x dot is going to be minus 2 pi sine pi 0. Okay? That's going to be what? 0. Okay. So y dot is going to be 8 pi sine 2 pi 0. That's still 0. And x dot dot is equal to minus 2 pi squared plus pi 0. That's minus 2 pi 0. And y dot dot will be equal to 16 pi squared plus 2 pi 0. 16 pi squared. Does it make sense? So therefore, you can get the velocity now. Velocity at time is equal to 0. Is equal to what? 0 I, Abby, plus 0 j. The velocity is also. Velocity is 0. Is it clear? Do you understand that? That means it started from rest. Does it make sense to you? How many body started from rest? The velocity at time t equal to 0 is 0. Is it clear? Is this clear? Alright. So the acceleration, how can you understand what I'm doing? Velocity is x dot I plus y dot u. X dot is 0, y dot is 0 at this time. So let's put them in. Is it clear? Over the 0 now, it doesn't matter. You get it, because it's 0. So this is going to give you, this is equal to minus 2 pi squared I plus 16 pi squared j. Is it clear? What is the unit now? Meters per second. Meters per second. So we can now obtain its magnitude and direction. So its x component is negative, its y component is positive. That means it's going to look this way. Acceleration is going to be given by this. X component is negative. That means we have something pointing in this direction. Abi? Now y component is positive. That's going to be something pointing in this direction. This should be significantly longer. Just so this is 16 pi square, this one is 2 pi square. Let's say we have something like this. Of course, we not draw to scale, it's just reasonable to have it. This is 2 pi square, this is 16 pi square. And we get this and this. Then we find out the angle it makes between x axis theta. So this is going to give us magnitude of acceleration. So our magnitude of acceleration is going to be equal to square root of x component 2 pi squared plus y component 16 pi squared. That will give us what? And theta will be equal to the tan inverse of opposite is 16 pi squared and adjacent is 2 pi squared, which is 16 pi squared over pi squared. That will be 16 over 2, tan inverse of 8. So theta is going to be equal to the first one?
159.1.
159.1 meters per second. This one?
Yeah.
82.87. That is 9. Therefore, acceleration equals to 159.1 meters per second square. And in this direction, direction 2.9 degrees. That is that about that. Is it clear? So with that, zero velocity, that is non-zero acceleration, and equal to 0. Is that reasonable? Does it make sense that velocity is 0 but acceleration is not 0? Does that make sense? I don't think so.
Mass, can it be that the maximum height already at that time?
I mean, they started with rest with a certain acceleration. Together. Instantaneous value, the value at an instance. Velocity is instantaneous velocity. That's the value at that particular time. Okay? Do you understand that? That does not mean it is not increasing. It might be increasing from 0 to something else. Do you understand that? That means if you get it at a later time, it will not be 0. Do you understand this? Yeah, that's the instantaneous value. It is 0 at an instant. Just like if you have a body, you have had a car start from rest before. Abi? When the car starts from rest, it's going to accelerate. Acceleration is not 0. Velocity was 0 at that instant. Do you understand that? Do you get that? So, it is the rate at which it is increasing. The rate at which the velocity is changing. Alright, so you can do the same thing now for t equal to 1.5 seconds. Do the B part. T equal to 1.5 seconds. The velocity, what did you get?
2 pi.
2 pi. 6.8.
Okay, my second.
6.28 meters per second.
I'm serious.
Acceleration is what?
Negative 1.
Yeah, 2 pi is 6.28 now.
No rush to answer into final. Just put numbers. Is this clear? Everybody got this? Okay. Alright, let's move on now. How many 10 minutes left? So let's see. I want you to solve from 11.92 to 11.96.
Where?
At home, assignment. 92 to 96. So 97 is a projectile motion problem. I want us to solve that problem. 92 to 96. So I will solve 9 and 2. Anywhere we get to. Yes, 11.97. An airplane used to drop water on brush fires. Bush fires. 11.97. The bush fires, Abby, but it doesn't matter. He's flying horizontally in a straight line at 350 kilometers per hour at an altitude of 80 meters. No altitude means height. Determine the distance d which the pilot should release the water so that it will hit the fire at b. It's a projectile motion problem. Listen very well, please. So you have this kind of situation to release at the point A and to go this way. Pay attention. This is just like the other half of the projectile motion. You understand what I'm saying? Right. So this is what you have here. So I can establish my coordinates from you. Establish your coordinate system. You can locate the origin anywhere you like. Okay? Just ensure that you stick with the notation or whatever sign convention is. This is our x direction and this is our y direction. Is that clear? So at the point A, I have this point A, right? This is point A, and this is point B. Pay attention. So I also have this distance has been given to me as 80 meters. As this height is 80 meters.
Yeah, you have to
And then this distance has been given as t. You want to find out what distance don't forget something. We have the initial velocity v naught. That the velocity with which it will be released from the top. Is that clear? So listen please, listen. This is the velocity with which it was released from the top. It was released with the velocity v naught. That's velocity v naught. Okay? And they said that velocity is 315 kilometers per hour. Convert to meters per second. Divide by 3.6. What does it give you? 315 divided by 3.6. 87.5 meters per second. Horizontal direction. Please pay attention. So when you have this kind of motion, listen, you know that the water is being released. Released will imply that the initial vertical component of velocity is 0. Is it clear? So the velocity we have here is the horizontal velocity, which is going to be equal to the velocity of the airplane. Is it making sense? Alright, because it is released just like I drop a pen from here. You say the initial velocity is 0 because it's going vertically. Is it making sense? The same thing is happening here, just that instead of going just vertically, it's also going simultaneously in the horizontal direction. Is it clear? And we have said that we will consider them as independent. Is it clear? So I will consider the vertical motion as though it was happening alone. If it was happening alone, then the vertical component of velocity will be 0 initially. Is it clear? Alright, so that means for this system, I have now separate the y component and the x component. So for the vertical component, the horizontal component. For the vertical component, I have v naught y equal to 0. Is that there?
Yeah.
Then I have v naught x to be equal to v naught. Is it correct? That is 87.5 meters per second. Does that make sense? I know that the horizontal component of motion is uniform motion, and the vertical component of motion is uniformly accelerated motion. Does that make sense? Okay, I know that the body was initially at this point A, and then finally at this point B. Is it clear? That means I can write y naught, initial vertical position, 80 meter, and y, that's the final position, is 0. Is it clear? Because this is the origin of our coordinate system. By the time it gets to this point, its y coordinate will be 0. Is it clear? At this position, its y coordinate was 80, and at this position, its y coordinate became 0. Is it clear? Okay, and then for x, initially, x naught is what? 0, and finally, x is what? D. You get that? Okay. So we can now write our equations of motion. So I know that y minus y naught should be equal to v naught yt minus 1 over 2 t squared. And for this, I know that x minus x naught should be equal to v naught x multiplied by 2. Is it making sense? Alright, so I have all of this, and then I know that this one is 0. When I substitute here, I'm going to get this y minus y naught, that's 0 minus 8c equal to this is 0 multiplied by c, minus 1 over 2 g t squared. So this tells me that minus 80 equal to minus 1 over 2 g t squared. This tells me that 80 is equal to, I'll say gt squared, gt squared is equal to 160. Is it clear? When I make substitution here, I'm going to have x, that is d, minus x naught, which is 0, equal to v naught x, which is 87.5. You know, I have to take care of the sign here also. It's positive because it's pointing the positive x direction. Is it clear? This was the negative x. I have to take care of that. Okay, so this is going to be 87.5 multiplied by t. So from here, I can make t the subject. Why? T is common to both of them. I can make t the subject here and substitute it here. Why? Because both components of motion occur simultaneously. Does it make sense to you? That means both components of motion occur at the same time. So I can make t the subject in one component and substitute it into the other components. Is it clear? Is this clear? So I can write that t is equal to d over 87.5. Is it clear? So I will then substitute this t into this expression. Does it make sense now? Yeah. Right. So therefore, I will have g multiplied by t, which is d over 87.5, to be equal to 160. G is acceleration due to gravity, which is 9.81. Abi? Okay, square, yeah. This is going to give me 9.81 multiplied by g squared divided by 87.5 squared equal to 160. So you can solve for d using that equation. Yeah, we're done. So that's going to be your final answer. What is it? I want to get the answer. That's what the answer is. 353 points. So d equals to 353 meters. So that is that. But how to the square root? Alright. So that means we are good to go. So we are done for today's class. So as assignment, another one, that was on general motion example now. On projectile motion, we did the two of them now. So should attempt to work on projectile motion. Some people have MSc class. 11.98 to 11.101. 11.98 to 101. Alright, that's all. For this week on Monday, make sure you register before you do so that I can have your videos and proceed to groups. can discuss when you can make a and solve problems.
Yeah.